Now, now this is a simple topic, but very important topic, carrying just 2 marks. But this topic result is again and again useful in many topics of not just this lesson, even in other lessons also of electricity, and even beyond electricity, even other branches of physics also. This is very useful. It's not a new topic, it's actually the same thing. For example, F is equal to ma is Newton's second law. From this equation directly we can write A is equal to F by m. So A is equal to F by m is something not different from Newton's second law. It's just another form of writing the equation F is equal to m. It's also the same thing. So it's directly modification of the defining equation for electric field vector. So electric field vector, we have learned that it's force per unit charge, F by Q naught. So that equation itself is modified. So but this is more useful than the defining equation E is equal to F by Q naught. Those definitions are the most powerful things in science and technology. A simple definition can have wide applications. So this is also one such example. Simple defining equation gives this particular equation, which is very useful in many situations. So what is this? So force acting on a charge Q in a uniform electric field. Now consider a uniform electric field. So uniform electric field consists of electric lines of force which are exactly parallel straight lines and which are equally spaced. Equally spaced means the spacing between two any adjacent lines of force will be exactly same. Here the spacing between first and second lines of force is say 2 units. Next second and third also 2 units. Third and fourth also 2 units. Now this uniform electric field, the electric field vector, is denoted as E. So because it's a vector, bar also can be used. So here also uniform electric field, its electric field vector is denoted as E or simply E bar also it can be written. So E bar is difficult to write. So I'll just put E later. I'll write E bar also, but now it's becoming a little congested here. So this is the electric field vector. So everywhere in a uniform electric field, the electric field vector will be exactly the same, both in magnitude and direction. That's the important thing. So in this electric field, at this point, supposing at this point we are taking a certain point, here you are putting a charge, say Q. A given charge Q is placed here. Always in an electric field, we have seen that a positive charge in an electric field experiences a force exactly in the direction of the electric field, but a negative charge experiences a force in the opposite direction. So this is a positive charge, so it experiences a force exactly in the direction of the electric field, but a negative charge experiences a force in the opposite direction. That's the important thing here. So Q being a positive charge, assuming this as a positive charge, it experiences a force exactly in the direction of the electric field. So now at every point in the uniform electric field, the strength of the electric field is same. E bar is exactly the same. But how is E bar defined? At any point, say at the same point position where the charge Q is placed. How is electric field vector defined? Force per unit charge. So this is defined as the electric field vector. So E bar. So if F is the force acting on a charge Q naught, supposing here we are putting a charge Q naught in the electric field, then the force divided by charge Q naught gives the force per unit charge, which itself is called as the strength of the electric field at the point where the charge Q naught is placed. This is what we have seen. This is the defining equation for the strength of the electric field already we have seen. But here, what is the charge that is placed here? Instead of Q naught, it is Q. So force acting on that is F. So F being a vector, F bar also can be written in place of F. So that force divided by charge will give the force per unit charge, which itself is called as the strength of the electric field or simply electric field vector by definition of the electric field vector E bar. So, but what is the charge placed here now? It is not Q naught but Q. So in place of Q naught, we'll put a Q. So F is by R is now the force acting on the charge Q. So only in place of Q naught we are putting Q. Then how much is the force if you want to find out? Simply Q take to the left hand side, we'll get the force. So therefore the force acting on the charge Q is simply Q into E bar. So this is the equation. So very simple equation. Force is simply given by charge into the strength of the electric field or strength of the uniform electric field. So any charge Q placed in uniform electric field experiences how much force? exactly given by the product of charge and the electric field vector E bar. So more charge is placed means more force it takes. Force is proportional to charge and also proportional to the strength of the electric field E bar. So charge is doubled, force gets doubled. Even electric field is doubled also, force will be getting doubled. So that's the simple relation. So this is a very, 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 very important equation. At the same time, it is also very, very simple. It's the same thing. E is equal to F by Q naught or F by Q. Then taking Q to the other side, we'll get this equation. But still, this has its own importance. It's even more important than the defining equation. Though it's actually derived from the defining equation in just one step, it's even more, it has even more powerful applications, many applications compared to the defining equation. So the derivation is actually very simple. Now consider Q to be a positive charge. Then force acting on it is Q into E bar. So in the same direction of the electric field. So force, whatever is the direction of the electric field vector, same is the direction of the force. What if it's a negative charge? We know that negative charge experience a force in the opposite direction of the electric field. So if you put a negative charge here, what is the force means? Minus QE bar. So minus QE bar means it is opposite to E bar. So electric field vector is a positive vector means force is coming negative. This simply means that it is opposite. So that way also this equation can be understood. So now the derivation is just in two steps. We are getting the derivation. Little two lines explanation should be given. So a charge Q is placed in a uniform electric field E bar as shown. So next, little another two lines is there, but there is no place here. So I'll do one thing. I'll just shift the equation a little down. And even this equation also, I'll just shift it a little down. So if F is the, so important thing is what is the direction of force you see? It's in the direction of the electric field because it's a positive charge. If F is the force on Q from definition of E, that means from definition of the electric field vector, electric field vector is nothing but force per unit charge. That is force divided by charge Q naught. This is a regular definition. Q naught is a symbol used in the regular definition, but the same Q naught is Q here. Therefore, we are getting this equation. Now, a very important thing about this equation is if Q is a positive charge, force is in the direction of the electric field, as can be seen here also. Q is positive means F and E has the same sign or same direction. And Q is negative means F and E are opposite. So E being positive, if E is taken as positive, force will be negative. Or if E is taken as negative, minus is already there because it's a negative charge. So minus of minus will be positive. So always F and E will have equal and opposites, that is exactly opposite signs. That means they are in opposite direction if Q is a negative charge. That's the meaning of this equation. So I'll just, that's also very important. So it can be taken as a note point. So note, so if Q is positive, F is in the direction of fielding. If Q is negative, F is opposite to fielding. That's the thing. So next topic is the moment of couple. But see here, actually there is no place here for the topic. So moment of couple, I'll just shift the side heading to the next page. So it's coming. The next page is actually coming in a moment. Yes, it has come. So this is the next page. the moment of couple. I'm dividing the page into two halves. So left half and right half. Okay, coming to the equation, coming to the side heading. Now this is the continuation of the dipole moment of a dipole actually. It's a continuation topic of the dipole moment topic, which we have seen two topics earlier. Immediate last topic was force acting on a charge in a uniform field. So this is also an application of this force acting on a charge in a uniform field. It's actually application of the or extension of the last two topics. But it's very important. This is actually almost the one of the most important topics. So it carries 5 marks to 4 marks. So 4 marks means it's actually a short answer question. 5 marks means it's a part of an essay question. So essay questions for many board exams carry about 8 marks. Some board exams only 5 marks. Essay questions, that's the maximum marks, 5 or 8. So in both cases, this will be useful whether it's given for 5 marks or 8. But always essay question, whether it's though it's carrying 8 marks, the big essay question, it consists of two parts, part A and part B in the 8 marks. A bit will be the real essay question, but carries only 5 marks. So every essay question in almost any board exam carries only 5 marks. 5 marks means just one diagram carries about 1.5 marks. One definition, 1 mark, 2.5 marks. Remaining 2.5 marks, just in 5 or 6 steps, it should be completed. So as short as possible, the derivation should be written. So coming to the topic, so moment of couple or torque. It is denoted by symbol C bar. So 5 marks to 4 marks. So moment of couple or torque C bar acting on a dipole in a uniform electric field. So what is this moment of couple or what is this torque? Why it acts on a dipole in uniform electric field? So this it can be understood from this simple diagram. Now consider a uniform electric field. In that uniform electric field, a dipole is placed. So what is a dipole? Already we have seen a pair of equal and opposite charges. So the diagram we have seen earlier, we'll just go back to the diagram. So this was the diagram of the electric dipole. Just see here, this is the dipole diagram. So a negative charge and positive charge, that is a pair of equal and opposite charges separated by fixed distance, is called as an electric dipole. So dipole has a very important quantity called as dipole moment. So what is that diagram also already we have completed. Just look at the diagram. So the dipole moment. Let's just see the dipole moment here. It's a vector quantity denoted as p bar. So its direction is always taken from the negative charge to the positive charge. So that's the dipole moment. So such an electric dipole, put it in a uniform electric field. So like this. So diagram will be like this somewhat. Now consider a uniform electric field like this. It's directed say upwards, or simply the direction can be taken as towards north, this way. I'll just draw the vector like this. So this is the uniform electric field. So uniform electric field means not just one line of force, many lines of force should be drawn. All the lines of force will be exactly parallel to each other and they'll be equally spaced. So usually uniform electric field we take it as horizontal. This way we take it as horizontal, rightwards, left to right, that is west to east direction, but it's taken from south to north direction. This way, south to north direction, here in this derivation. Now the important thing is exactly in this uniform electric field, the strength of the electric field is known as E bar. It's directed from south to north. Take the north, south, east, west directions. I'll draw a rough column here. So north, south, east, west directions like this. This is north, this is south. So this is east and this is west. Always north, south, east, west directions. Very important thing about north, south, east, west direction. They are considered on the ground, on the surface of the earth. So surface of the earth is also called as horizontal. Any plane parallel to the surface of the earth, parallel to the ground, is also called as horizontal. So we are considering in a horizontal plane the north, south, east, west direction. In this horizontal plane only, we are imagining the electric field. Now put a dipole here. How is the dipole placed? Just see here, this way. So this is the positive charge of the dipole, or this is the one charge of the dipole. So both the charges of the dipole are equal and opposite. So this is taken as positive, means this will be negative. If this is taken as negative, this, so I'm taking the negative charge first here. So this way, this is the negative charge of the dipole. So minus q. So positive charge is somewhere here, this way. So this is the positive charge of the dipole. So it is plus q. So these two are separated by a fixed distance. So this fixed distance is called as the length of the dipole. So this is the simple dipole. So its dipole moment is what? Its dipole moment is denoted by symbol P or P bar. It's directed from the negative charge to the positive charge. So this is the electric dipole having dipole moment P bar. So P bar I'll write as clearly so that it looks like real small p. So some textbooks use small p for the dipole moment, some textbooks use capital P. Any symbol can be used, so it doesn't matter. Now the important thing is this dipole is placed not exactly in the direction of the electric field or not exactly perpendicular to the electric field, but inclined manner it's placed, making an angle of inclination theta. So this is the direction of the dipole moment, negative charge to the positive charge, and this is the direction of the electric field from southwards to from south to northwards. So the angle between these two directions is simply denoted as theta. Now this is a uniform electric field. Uniform electric field means lines of force. Electric lines of force will be parallel straight lines. So many other lines of force can be drawn. So I'm drawing another line of force. Just see here. This is another line of force, and next another line of force. Still I'm, so just a moment please. The important thing is lines of force means they'll have directions. So they are arrows. They are indicated by arrows. So I've drawn about so this way, and next here I'm drawing so that the charges are actually not disturbed. Without passing through the charges, I'm drawing the lines of force. The same way it has to be drawn. So during explanation itself, try to draw the diagram, but compulsory listen to each and every word. So the lines of force are parallel straight lines exactly in the same direction, but equally spaced. That's the important thing about a uniform electric field. Now the direction of the, just observe here, the dipole moment vector p bar, it's also a vector quantity. Its direction is not clearly visible in the diagram, so I'll just show the direction by means of this arrowhead a little away from the line of force, so it's more clear. Now the important thing is this dipole positive charge experiences a force exactly in the direction of the electric field. That's what we have seen. A positive charge experiences a force in the direction of the electric field. Here is south to north, so force experienced by the positive charge also will be south to north. So that force is actually shown here this way. So this is the force. So this is the force. But how much force experienced by charge q? Already we have seen it is QE. This is the force experienced by any charge q. But the force experienced by negative charge is minus QE. That's opposite to the direction of the electric field. So this charge is minus q. So I'll just write this minus q more clearly, little away from the charge, minus q, so that the force can be drawn easily, because the force is directed downwards. Just see here, the force experienced by the negative charge is directed downwards this way. That means opposite to the electric field. So how much is this force? Minus QE. So this way, minus QE force is experienced by the negative charge. Now it can be clearly seen that both the forces experienced by the two charges of the dipole are equal and opposite. Such an equal and opposite force, pair of forces, is called as a couple of forces. So this is a couple of forces. So what is the importance of a couple of forces? The importance of a couple of forces is a couple of forces acting on any body will produce a turning effect. How it produces a turning effect? Now you take a tap. Now this is a tap. So tap, this is a regular tap, it looks like this. This is how a regular tap looks like. Now how do we turn a tap? With the two fingers. One finger you'll be holding, with the forefinger you will be holding this side, with the thumb you will be holding this side, and with the forefinger this way. Supposing this is the forefinger, so this way you are holding it. Thumb you are holding it like this, and then with the forefinger you'll apply a force into the board, into the screen. Thumb you're applying a force in the opposite direction this way. So I'll just write this more clearly. So this is the tap. So with one finger you just push this end of the tab. This is actually the knob of the tab. You'll apply force directed, say, into the board, directed into the board, and with the thumb you'll apply force in the opposite direction. So this F means this is minus F. So such a couple of forces. This is simply called as equal and opposite forces. A pair of equal and opposite forces acting on a body, simply called as a simple words. I'm not giving the definition. Exact definition is always perfect. So couple of forces is defined more exactly, but roughly the meaning is a pair of equal and opposite forces. So this pair of equal and opposite forces, whenever acts on a body, a turning effect is produced. So as seen from the top, for example, from the top if we are seeing, so the force is this way, in this direction it's acting F, minus F is acting opposite. So from the top if we see, this object turns, say, anti-clockwise in this case situation. As we see from the top, it turns anti-clockwise this way. So this turning effect produced by couple is called as moment of couple. It is simply called as moment. The word moment means turning effect. So moment of couple. So moment of couple, moment of, two words are there. So because it's difficult to pronounce two words, moment of, it's also called as in single word torque. Torque due to couple. So torque means turning effect of a couple of forces. So here also on the electric dipole also a couple of forces are acting, plus QE and minus QE. So they produce a turning effect. So as we see, the that is dipole, electric dipole in this particular situation, it tries to turn anti-clockwise this way. An anti-clockwise turning effect is produced. So this moment of couple or torque due to couple, always torque due to a couple is found to be vector quantity. So its direction, only two directions are possible for torque or couple, torque due to a couple, or simply torque or moment of couple. One is anti-clockwise direction, one is clockwise direction. So this is anti-clockwise direction going this way. So what happens is it tries to turn in this direction. So in this direction it's trying to turn means the positive charge actually. So this here, this angle, particular angle, you just observe this angle. As it turns this way, the positive charge is somewhat going more towards north, and the negative charge is coming towards south. This position you call it as south position. It's trying to come towards south. That way it's rotating. That means this angle theta is actually tending to decrease. So that's what the turning effect due to the couple is actually producing this kind of result. The angle theta tends to decrease, and finally what happens is the dipole, it goes on turning, and finally it comes to rest. It comes into the direction of the field. So once it comes to into the direction of the field, what will happen? That can be clearly understood by deriving a very simple formula. That formula is nothing but the expression or the formula for the moment of couple. That is the main aim of this particular derivation. Just look at the derivation side heading. See here, moment of couple or torque C acting on a dipole in a uniform electric field. So in the uniform electric field, when it is particularly making an angle theta with the electric field, the dipole moment or the length of the electric dipole is making an angle theta, how much couple or how much moment of couple is acting, that is what is required. If we derive that one, we already got the direction here. The direction in this particular diagram is anti-clockwise. It's trying to rotate the dipole, the moment of couple C bar, because it's a moment of couple is always a vector quantity. It's denoted C, couple starts with the letter C, that's why it's denoted by symbol C. Because it's a vector quantity, C bar symbol is used, bar is used for the, always for any vector like electric field vector, or force vector, bar is used. So here bar is used. Now just observe here. So its main result is main effect is the moment of couple is trying to turn the dipole into the direction of the field. It's tending to it's trying to rotate the couple in such a way that it's trying to rotate the dipole in such a way that the angle theta decreases. This is very 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 important. Always a moment of couple acting on a dipole in electric field always tends to rotate the dipole into the direction of the field till it becomes parallel to the field. So why it becomes parallel to the field? So finally, once it becomes parallel to the field, there it stops. There it will be finally stopping. It's exactly like a bar magnet. The directional property of bar magnet when it's fully suspended, exactly like the dipole is fully suspended in a horizontal plane, like this plane, which can be taken as the plane of the that is plane parallel to the ground. So because north south direction, east west direction are considered only in the horizontal plane. So in such a horizontal plane we are putting the dipole, like a tabletop we are putting the dipole. So the field is parallel to this entire field is parallel to the tabletop, a horizontal surface. So a bar magnet also, if we are suspending in such a horizontal plane by means of a thread, exactly like this. So thread is actually suspended at the center. Then the bar magnet also turns into the direction of the magnetic field till it finally becomes parallel to the magnetic field. Earth's magnetic field is always directed from, just observe this north-south direction. Earth's magnetic field is always directed from south to north. So a bar magnet suspended in this way, parallel to the ground, always exactly in this direction, always comes to rest in the south-north direction. The reason is direction of the magnetic field is from south to north. So this is called as the directional property of a magnet. The same thing happens here. Now the question is, once it comes parallel to the field, why it comes to rest there? This reason already I said, it depends on the equation for or expression for the moment of couple. So how to find out the moment of couple? Easily it can be found out. So always whenever a couple of forces acts, so this is a rough column, very simple thing, very simple example of couple of forces acting on the two ends of a tap when we try to turn it. So with the forefinger, we'll apply force directed into the plane of the board here, whiteboard here, and with the thumb, actually we'll be applying a force in the opposite direction. That's how we turn a tap. So just try to turn a tap and observe the forefinger and thumb. Forefinger pushes the one end of the tap in one direction, means thumb pushes it in the opposite direction. Just observe it carefully. Always definitions, scientific definitions are given by scientists, were given by scientists by careful observation of real life situations. The best way to understand a real life situation without really doing the experiment is by drawing the line diagram. So in the line diagram, everything will be shown clearly. What is the direction of F? What is the direction of minus F? Everything. Any doubt is there, immediately you have to go back to the real life example. Just observe a tap how you are turning it. This is how we will be turning it. It will become very clear. Then the diagram can be understood more clearly. And once the diagram is represented, always looking at the diagram, everything can be revised in a fraction of a second. So that's the importance of scientific diagrams or line diagrams. So what is a line diagram? A simple diagram consisting of lines, important things represented by lines like forces. Or for example, you have say the Young's double slit experiment. Just see here, a Young's double slit experiment, important thing is two slits are there. So what will be passing through the two slits? Light waves will be passing. So these two light waves coming from the two slits, they'll be going forward and they'll be superimposing on a screen. There, if they cancel each other, a dark band is formed. So what is really happening? You are showing by line diagram. Line diagram, what is represented? What is really taking place? Light rays moving towards the screen and intersecting there. That is what is happening. That's what is shown in line diagram. But if we take a photograph of this, we can't see anything except for the bright and dark bands. We can't see what is really happening. The rays can't be seen in a photograph, because light rays, though they cause vision, they are actually invisible. They are really are invisible, because if they are visible, we can't see the objects. We'll be seeing only light. Without light, we'll be, instead of light, we see the objects on which light falls. So we can see the objects, but we can't see the light, you see. That's why light is said to be invisible. Though they are helping in vision, really, strictly speaking, they are invisible. Just think of what I am saying. So all these things were really explained by scientists clearly. So just think a little. So I'm not explaining much. Any doubt is there? Just rewind the video a little, 1 minute, only half minute. You just rewind and just hear it here once again. So light rays are really invisible, but objects on which light is incident, light falls, the objects will become visible because of the light. Just think of it a little. So that's the power of line diagrams. What is really taking place, that is clearly shown in the line diagram, that will never be possible by a that's never shown by a three-dimensional photograph. So that's the thing. So I'm just giving it as an example. So many of column points are, but this will use this Young's double slit experiment in other topics also, again also later. So Young's double slit experiment, where you have seen firstly in the, that is most probably in the ninth class or 10th class, I think. So again, you have this in your syllabus, present syllabus also. So we'll see that again. So whatever things we are seeing here are simple, nowhere any complication is there.